listen-only mode.
All right, good morning everybody. My name is Adrian Jensen with Predictive Engineering and Applied CX, and this is another one of our online technical seminars with FEMAP and Nastran. Also online I have Kyle Hamilton. And
hi everybody.
Thanks Kyle. He's going to be helping us out with some of the post-processing later on. George Laird is also on the line. George, you want to say hi?
Hello, I'm the principal and I'll be hanging out in the background answering questions, and you guys are going to notice the setup is that the ability to query questions into us, and I'll try to do my best to answer them. So
yeah.
Welcome to the seminar.
Thanks, George. Yeah, if you guys have been on these before, you'll notice there's a little questions section of the GoToWebinar software, so you can punch in questions there. And it's going to be pretty packed in, so if we don't get to your questions during the webinar, we'll follow up afterwards. I'm thinking there's going to be a lot to cover and a lot of questions. So we'll try to incorporate those questions and answers into the documentation here once we get this all uploaded. I also wanted to introduce Eric Barber. He is our account manager here at Applied. And Eric, you on the line?
I am. Good morning. My quick introduction for those of you that have sat on these webinars before, as you know, for customers currently, Applied CX is the software training arm for predictive engineering along with Sherpa Design. So we sell and support the software that these guys are using every day. In this case, it's FEMAP, Nastran, and along those lines, on the Sherpa Design side, they're utilizing NXCAD. They have their own machine shop with a Mori 5-axis machine and utilizing NXCAM. So those guys are able to support our software clients, the fact that, once again, they're using that software each and every day. For those of you that are new to us, the customers already know that we've got a vast online technical resources available for our customers. The fact that we really take great pride in providing outstanding technical support to our clients. Our team here is tens of thousands of hours actually using the software for real-world engineering challenges, and that's one of the reasons why FEMAP development team looks to our team to test the new beta version, which is on their desks currently. For those of you that are not clients, you can be supported by the true experts for the same cost. You're not being kicked to GTech, so to speak. In terms of the continuing education lines, Adrian has a new FEMAP API course, which will be available online at the end of the month. For those of you who are interested on any of these fronts, feel free to give me a call, drop me an email, any interest in our trainings, moving your maintenance, or simply want to take the FEMAP plunge, if you will. Back to you, Adrian.
Excellent. Thanks, Eric. All right, so if I do my job right here today, you guys should be left with all sorts of fear, uncertainty, and doubt. But that's okay, because welds are a tricky thing. I reached out to several friends and colleagues when I started this, and they just everyone's like, wow, massive topic. So I want to kind of focus in on the FEMAP front, how to prepare your model, how to interrogate your model, how to set it up so that you're going to end up with results that you can use to generate real numbers for you here. So we'll have lots of references for you guys. There'll be lots of reading. You're probably going to be buying some books if you really want to dig into the weld fatigue side of things after this seminar. But I wanted to start out with this little guy here, which I've made several attempts at getting my most realistic, in-depth weld simulation here. And this isn't entirely accurate because we don't really capture the axial movement of the weld along here. But what we've got is, starting out with a very hot weld material, low modulus elasticity, low yield stress, and as things cool, they contract. You're going to see through these stresses here that our weld material reaches up in the yield stresses. We get some warping out of this from the different thermal contraction. This was a lot of work, and the other thing about this is it's probably not very accurate. Having material properties over a huge temperature range is difficult to get. The loads themselves, the temperature loads that I put into this are an approximation. I start out with a hot temperature, but different conditions can lead to different cooling rates. So a lot of people see this and this is what I want to do. I want to get as detailed and accurate as possible with my welds, but in reality it's just not feasible. It takes a lot of work, and it's not going to be that accurate. You're only as accurate as your loads are. So what we're going to do, as much fun as this is, we're going to step back and take a look at some more simplified methods that are going to give you models that run quickly, and then also some things to avoid so you're not chasing your tail too much here. So a few things that I want to introduce. One, again, loads. Your models are really going to be as accurate as your loads that you put into them. Two is when you get into the fatigue side of things, is the scatter. There's a lot of scatter there. So we're not necessarily trying to get the exact right answer. It's based on probability. We're trying to get close as we can given the information we have. A few other things are, especially concerning fatigue, is the slope of the fatigue curve. Small changes in stress are going to be huge changes in fatigue life. So getting accurate stresses is important, but we also have to remember that there's a lot of error involved there. And then finally is the weld quality or the weld details. You can give the exact same drawing to two different welders. You're going to end up with different welds, slightly different. So we're not focusing on getting all those exact details right. We're focusing on the big picture and getting as close as we can. Here's the outline. I'm going to start with some modeling, different model setups that you want to keep in mind. Then we'll move on to meshing and some of the detailed meshing methods that we'll use for welds. And then we'll get into post-processing, some of the different methods that you can use for stresses and then also forces extracted from the model. So let's start out with our modeling here. And what I've got, some simple examples here. And we rarely do full solid models of the weld. Again, I can generate stresses in here, but it's not totally going to be accurate because I can't always capture all the details of the weld. Also the residual stresses from the welding, and any sort of warping probably isn't going to be incorporated into my model. But what I wanted to do with this was the big picture, full penetration versus fillet welding. You can see here, same structure, same loading and constraints. We have a pretty significant change in stress between the two. Let me just turn on my stress values again. So let's first look at this one. This is what I would consider a full penetration weld. We have continuous mesh through our part here. We switch over to the other one, we jump up in stress significantly, and that's because this is only partial penetration or fillet welded. So let's take a quick look at the geometry to how I set this up. So these are hex mesh parts, and you're going to see a lot of hex meshing and surface meshing in this workshop. So if you guys need some more information, we can point you to some other seminars to get you up to speed on that. But what I wanted to do here was the bottom surface of this plate coming into this T-junction, whether or not the nodes on that surface get merged or not, is going to change the load path significantly. So here you can see continuous mesh. Here I disabled merging on that face. When you set up hex meshing, it's automatically going to match faces and merge nodes. So what I wanted to say is, all right, this has small fillet welds on the outside. My load is going to transfer through the weld, and I'm not going to be able to carry any sort of tensile load across this free face. So I set up my mesh sizing, hex meshing like I normally do. Then I came into mesh control, approach on surface, and you can actually manually control individual surfaces, whether they're linked or not. So by default, they would be linked, the nodes would be merged, and we'd end up with one continuous mesh. I came in here, turned the matched mesh, turned it off, and you can see with my free edge plot, see that dark line there? That's showing me that we have a free face. So this is kind of the first step here. You have to think about, do I have full penetration welds? Is the stress in my material, my parent material, going to be about the same as the stress in the weld? Or am I choking down and forcing all of my load to pass through small areas like this here? Okay. Next, in terms of idealization, is the different possible weld shapes that you could have. So we've ran through several different models here. We have sharp corner, we have a fillet. This would be kind of the convex weld. And then we have our ideal weld, which is just a chamfer here. So we can go through this and look at the different regions here and our maximum stress values. I'll turn my legend back on. So we've got the same material, same loading, and as you cycle through these different ones, 18 KSI, 15 KSI, 16, and 16, we're changing our stress values quite a bit. And I don't want this to concern you because we're not really going to be looking at stress values right at these notch for any of the setups here. What we want to focus on is setting up the model where we can recover stresses away from those sharp corners or away from those singularities. So I've set up different groups here so I can contour just the elements in those groups. And you can see once I move away from my sharp edges or our discontinuities, we end up with much more consistent stresses. So I think the big takeaway from this, how you're going to idealize the actual shape of your weld, if you've got large thick plates, small fillet welds, you want to be aware that the way you idealize the welds could affect the load transfer through your model. And that's really the first step. Before we get into the actual stresses, we want to make sure that we have the right stiffness and the right load transfer. But beyond that, once we get into investigating stresses, a lot of the post-processing methods aren't going to have you pulling right at the weld. So it's not quite so critical. And as we'll see in a little bit, the stresses right at those notches is not something you want to chase. You can spend endless amounts of time trying to get convergence there, and it's just not going to happen for you. All right, so let's move on to 2D elements. This is probably the most common thing that people are using for large structures, large thin-walled welded structures. And a lot of questions that I hear commonly is, how do I connect these two different plates? You start out with your solid geometry, you mid-surface the parts, and then you have to connect the parts in different ways. So I just set up an array of different configurations here. Along the top, we have a thick backdrop, and we've welded on a thin bar. I've got a solid mesh here, continuous mesh. I use this sort of as my control. I figure I've got 3D resolution in terms of at least my stiffness, my deflection. This will be my baseline. And then as we move on to the left here, if I turn on thickness, it'll be a bit more apparent that this next one over, we've merged the nodes. So for our geometry, we've created one continuous sheet solid. The nodes merge along that edge, and we don't really have to worry about the connection. If we do the setup in the geometry correctly, we're automatically going to be connecting these different parts. So what we have here, this is a sheet solid, one continuous solid made up of multiple surfaces. So even though we don't have any actual thickness to this part, we still call it a solid because it's all one part. Moving down the line, the next one is a glued connection. You can see how the mesh there does not match up. So I didn't bother connecting these two solids together. I mid-surfaced them, I meshed them, and then I connected them using connections. You can see here in the model info tree. So this is a glued connection. Connections are the same sort of entities used for contact. And I've set up here in the NX options, glued connection type, and I've just gone with the defaults. My connection regions, this is really where the trick comes in with plate elements. You'd set up your surface that you want to weld onto, just like any other connection region. You can choose by element face, by geometric surface, and your output is going to be elements or element faces. So it's good to remember, regardless of the technique that you use, at the end of the day, you're just submitting element faces to NX Nastran. The edge, this is where things get a little bit trickier in terms of setup. You want to make sure, whether you select by curve, elements, or nodes, that your output is now nodes. So this is what really specifies this as an edge glue connection. We're going to be tying the nodes along this edge here to the element faces on the back plate. So does it really matter which method we use? Do we get pretty similar results? So like I said, I set up an array of different thicknesses here, and I found that with a thick back plate and attaching a thin bar here, in terms of deflections, both methods matched up with the solid element pretty well. I didn't see a huge difference. So one, you might have a bit more work in terms of setting up the geometry. One, you have a bit more work in terms of setting up the glued connections. At the end of the day, you end up with pretty similar results. So I wanted to dig a bit deeper. Which one of these methods is better, or is there certain scenarios in which you'd use different methods? So if we move down to the thick connection here, again, both the glued and the merged nodes pretty similar. But we're starting to get to the phase where the thickness of our plate is overlapping quite a few elements on our backdrop here. And in this case, it turns out that both the back plate and our bar are thick enough that we're not really missing out on too much of the stiffness of that connection here. But my third example, we have a thin back plate and a thick welded bar. And when we take a look at this one, we can see that we're getting a lot more deflection out of our merged nodes than we are out of our glued connection. And furthermore, our glued connection matches up with our solid model much better. If we take a look at the glue forces, this will make a bit more sense. So from your post-processing, whether you want to use post data here or the post-processing toolbox, I'm going to come down to my glue force, total glue force. And what you can see here is, even though I've got a 2D element, it's actually accounting for that thickness and distributing that load over a larger selection of elements here. So this is the argument for using glued connections, especially when you're working with two different plates with very different thicknesses here. So a couple of different options in terms of setting up your model, getting those stiffnesses right, and getting the correct load transfer between your parts. All right, the next one I want to talk about is weld zones. Whether you have different areas in your model that you want to define with different material properties, or simply just subdivide your model for organization later on, these weld zones can be very useful. And this is kind of similar to what we saw with this previous example here. Let's see. Pardon me. Good, glued. All right, let me open up this new model real quick. Weld zones. All right, so what I've got a pressure vessel, and we're taking a solid 3D part and idealizing it with 2D elements. And whenever you have this sharp intersection between these, you're going to end up with a singularity at that sharp intersection. So this is something we'll talk about more in a minute, but you can refine the mesh and watch the stresses climb higher and higher. So you never really want to chase the stresses right at that sharp intersection. Different codes or different guidelines will give you different values of areas or distances away from that discontinuity to recover your stresses. This is an example of the ASME pressure vessel code recommendation. So I can turn off my geometry and my thickness. You can see I have 2D plate elements here. And within this region next to the singularity, or next to this sharp corner, I've set up a different material and different properties. Now, I'm not using different material properties. They have the same modulus. I'm not worried about yield stress or any of that. This is going to be a linear model. The reason I'm doing this is simply for model organization. So I can choose to contour on different materials or different properties. As far as the actual sizing of this area, you can see that I put this curve right at the toe of my weld. So you would move out half the thickness of your intersecting plate, half your thickness there, and then the distance of your weld leg. You can set up these regions on your model even if you already have a mesh part using the meshing toolbox. What I did for this one was geometry editing, and I did project curve. You can draw a curve either from CAD geometry or draw a curve on the work plane and use this to project it down onto your mesh, creating these different regions. So this one again is the weld zone. You could use this for a heat affected zone. Maybe you're working with aluminum and you might have different yield strengths in different areas. And of course it helps out with controlling your overall mesh quality. So once we have these imprinted into the sheet solid geometry, I mesh my part and I use different materials and properties, and I have analysis results. I create different groups of my different materials. So I could say group operations, generate materials, and I'm going to choose my standard material. So that's going to exclude all of the elements with the weld material. Okay, so I've got here under groups, I can say I've got duplicate groups. We can use just this one. Now I only want to show my stresses on this group here. So from post-processing, I go into contour and I use this option, show on groups, and you can either choose to show it on the full model. You can choose a specific group, or you can choose an active group. So the active group is nice. When I was looking at these different weld shape idealizations, I had all of these different groups, either the individual solids, you can see these groups here, or just subsections with just portions of the mesh. So this is a great way to provide information about your model to show your stresses, still showing the complete structure, but only contouring over the portions you want and eliminating those singularity stresses from your contour plot. Now, I don't really ever like to hide information when I'm, describing my models or my results. So when I go through documentation, I'll usually show the, here's the full field stresses. You can describe that, oh, this sharp corner is going to be a singularity. Moving away from these singularities, here's our stresses at X distance. A lot of the codes or guidelines that I was looking at, if not using the toe of the weld, it might be one thickness, your plate thickness away from the singularity. All right, so why do we want to avoid stresses at the weld? Let's take a look at a model where we've got the same exact setup, but we've got different mesh densities. So if we start here with the coarse model around 50 KSI, and you say, is this real? It's not quite at the corner there. Maybe I'll refine this mesh and take a closer look. We reduce the mesh size, we see our stresses go up. We do the same, they continue up, and so on. So you can continue to do this and continue to watch the stresses increase. Now, like we saw with that last model, we're covering the stresses away from the discontinuity. You will reach convergence. You can hit a certain mesh size, which will give you a stress value. You can increase the mesh density, and the stress value won't change. Of course, that's not going to happen at these sharp corners. So this is really the foundation of a lot of these methods where we don't want to focus at our sharp notch stresses. We want to set up our model so that we can recover stresses in some area that we can converge. You can perform this same mesh convergence study with hex elements, plate elements. You might end up with different asymptotes in those mesh convergence studies, but the consistent thing is you don't end up with a true converged stress value at those sharp reentrants. Okay, another question I get a lot regarding meshing is how do you connect dissimilar mesh types? We can't really afford to use these 3D representations, whether we put in a sharp corner or not, for all of our modeling. You can see a simple little model here, and I'm ending up, hundreds of thousands of nodes. When you're working on a full-scale structure, you just can't do this. You're going to want to use a combination of solids, plates, and beams. And transitioning from one of those elements to another is always a little bit tricky. So one method that we saw already, plates to plates, you can use the glued method there. You could also use that same glued method for plates to solids. So let's take a look at connecting dissimilar mesh types. So I chose a little I-beam for my example here. And again, I'm using my solid model as our baseline. And let's start out by talking about plate to solid connection. So your solid elements only have 3 degrees of freedom, 3 translational degrees of freedom, whereas your plates or beams are going to have all 6. So if you simply merge nodes along this line here, that's going to act like a hinged connection. We're not going to be transferring local moments. We'll get our overall moment from our I-beam resolved into positive and negative z-forces, but we're not going to capture that local bending right at that. We're going to have a hinge point. So one method that we could use is to actually embed our plate elements into our solid elements. And if I turn off my thickness in my elements, you can see that I've prepared this geometry such that I have one overlapping plate element inside of my hex element. So that's going to allow me to carry that local bending through multiple elements through the depth. The downside of this is it's a lot of work. You can see how I've sliced up this solid so that I can get the nodes to align and merge one element deep. The other option, which I don't have shown here, is you can use a flange. This is more common for me when I'm switching from solid to plate elements along some sort of structural member. So maybe you want to do a solid element at the connection, and then further down the line here you want to switch from a solid to a plate. And the idea here is that you would have your solid elements, probably multiple elements through thickness, and you have your plate elements here. Now, if you've got an end load on your plate element, how do you resolve this moment? What we've done in the past is we've put a little flange on the end of our plate here. That way you can merge multiple elements on that flange with the elements on the end of your solid element face here. That kind of opens up the question, how thick do you make your flange? I've generally used the same thickness as the rest of my plate, but as with all of these topics, it's good to explore the different thickness values, explore the different techniques, and see where the sensitivity really is. What you like to see is using a range of different thickness values, not seeing a huge range of stresses, letting you know that the model is kind of insensitive to this specific parameter. Now, again, this requires quite a bit of setup work and is not always the most useful way to use your time. So again, this is something where glued connections might be the way to go. Just like we glued plate edge to plate surface, you can also glue plate edge to solid element surface. We saw before that it does a great job of capturing the stiffness values, incorporating the thickness of our elements. And so it could be easier to set up and more accurate in terms of your actual stiffness and load transfer. All right, now let's move on to a beam to solid connection. So we run into this same problem here where our beam is going to have 6 degrees of freedom, Our solid elements are only going to have 3. So if you simply connect your beam in at a single node here, you're going to have effectively a spherical joint. You're not going to be able to transfer any torque or moment through that connection. So you could do what I've done with the plate elements, bury in one element deep, but we run into another problem is you're concentrating all of the load from the beam onto a single node on your solid mesh here. So what I ended up doing was connecting the two with an RBE2, or a rigid body element. And you can see when I turn off my thickness, here's my rigid element, and I simply attach to nodes along the profile of my I-beam. So I don't need to rely on any rotational degrees of freedom of my connected elements. I'm going to distribute that load. That moment will be resolved into normal forces or in-plane forces in the case of a torque load. And I'm going to get a better kind of approximation of my stiffness here. So when you guys log on and download these model files, you can see playing with the different types of loads, compare the deflection of our beam elements, plate elements, and solid elements, and see how close we're getting in terms of stiffness and load transfer. Again, we're not always focused deeply on the stresses at the connection, but getting the right forces or the right far field stresses. So let's do a contour, and I'm going to contour my deflection. For any of these models that you want to explore, convergence or using different techniques and want to compare deflection values, my go-to post-processing combination here is the entity info window and the selector. So the selector, you'll set, in the case of looking at translations, you would set to node. Your entity info here, if you guys don't see this on your FEMAP install, it's just another one of the panes used to organize FEMAP, and you can turn it on under Tools, Entity Info. And what I like to do is hold down the Control key and roll that mouse wheel, make the text a little bit bigger. And so here, if our model is deformed, we can use this tool to compare our nodal translations from one to the other. So translation in T2, we've got 0.11, 0.11, and our last one here, 0.109. So I'm getting really consistent deflection values even though I've got 3 totally separate modeling approaches here. And as you can imagine, the numerical cost of my beam element idealization here is going to be much lower than a full solid mesh. So you can save some time, save some nodes, get a faster running model. You just have to keep in mind the way that load is transferred from one section to another. How is that load going to be transferred in your actual welded part? All right, I've got one more meshing example here, and that is for the fillet welds. Let's go back to our pressure vessel example. Now, when I pass on to Kyle, he's going to describe how to extract some of the forces from your model, and rather than focusing on the stresses for a fatigue analysis, let's say the first step is simply sizing the welds. How big of a weld do I need on my part? Well, you would model up the different components, you would extract the forces from those components, and then you can use hand calculations to give you a rough idea of what sort of weld size that you're going to want there. Some of these hand calculations, especially for a single-sided fillet weld, imagine this pre-pad or this belly band on the outside of my pressure vessel here, they don't provide a way to resolve bending moment in a single-sided fillet weld. So let's imagine this part here. Our fillet weld is here. If we hadn't welded the other side and we have moment here, you could imagine that moment would just open up this fillet weld with very little problem. We basically have a pre-existing crack on the backside of this fillet weld. So you look at the hand calculations, they're not going to give you a way to size that weld based on a moment around this axis, because that weld really shouldn't be carrying moment. So in our model, it's not quite as much of an issue because we have welds on both sides. But how do I actually model that weld in FEMAP? What I've done here, let me turn off my thickness, is you can see these tiny little white lines, and those are rigid elements. And if I edit one of these rigid elements, you can see that it only has the 3 translational degrees of freedom. So we're not allowing that welded connection to carry that moment. Just like that fillet weld, yes, it's going to work well for transferring normal loads or shear loads, but once you start bending on it, it's going to open right up. We're capturing that effect with the idealization of these rigid elements. So obviously you don't want to walk through and snap these in one by one. So let me show you how to set this up. If I get rid of these rigid elements, my procedure is mesh, connect, closest link. The first step is to choose a group of nodes to generate the connection from, and I'm going to choose by curve. So I'll choose the 2 curves on the actual pressure vessel itself. You can see FEMAP is grabbing all the nodes on those curves for me. And then I select the nodes that I want to generate connections to. Again, I'll use this on curve method. And finally, we choose what type of connection we want. We could put in beam elements, we could put in constraint equations, C-bush elements. There's a variety of options here, but what I did, I chose rigid elements, and I only chose the translational degrees of freedom. And that's it. You can see it finds the closest pairs and snaps those in together. One thing to be aware of when you're working with this sort of weld connection setup is the fact these are rigid elements. These are constraint equations. So if you're working with a symmetry model like I have here, you don't want to constrain the dependent node of an RBE2. It'll give you a fatal error. So you might have to come in and be aware when you're applying your constraints that you do have constraint equations or rigid elements in your model already. Nice thing about the free body diagram toolbox, extracting forces here, there is a free body contribution for rigid elements. So soon we'll be talking about setting up these free bodies, and you can see you can choose elemental forces or constraint equation or multi-point constraint forces for your rigid elements. Okay, so we've got all of these different modeling techniques and meshing techniques. We know how to actually grab this information or grab our solid geometry, convert it into efficient FE model. What do we do once we actually have stresses? So there's 2 major categories. We have the nominal stress methods or the extrapolated stress methods. And neither of these are going to use stresses at those sharp discontinuities. Our nominal stress method is something you could imagine in our little T-joint example. You'd be taking your membrane stress, so let's say we've got 2 plates connected here. You would be taking your membrane or your linear through thickness stress. You would also be taking your bending or your surface stress, and you would actually be using special SN curves, depending on the code. ASME is one example. Special SN curves where you can recover your stress either at the toe of the weld or some specified distance, and then apply the stresses, the nominal stresses in your plate using those special SN curves. Some of the other options are the extrapolated stress method. So again, you're choosing your stresses, you're choosing to recover your stresses away from that sharp intersection, that discontinuity here. and you can actually extrapolate that information towards the toe of your weld or towards your hotspot. And again, there's going to be special modified SN curves based on the different types of joints. I'll attach some references for you guys when we upload this package, and you'll see that for a lot of these methods, you're going to choose your SN curves based on the type of joint. There'll be, especially in the nominal methods, there'll be different methods for T-joints, butt welded joints. Different weld categories are going to have different procedures. Okay, we are getting close to the end. I want to give Kyle some time for some actual hands-on post-processing. So let me transfer that over to you, and we'll get some more examples.
All right, let's take a look at some examples here. So the first thing we'll look at is using Blodgett's method for evaluating our welded area as a line. And this is really useful because a lot of the time when you're looking at your welded area stresses, you might not necessarily know what your weld sizing needs to be. Maybe you're trying to evaluate whether it's a solid weld or whether you can do an intermittent weld. And that makes it kind of tricky to directly calculate your stresses based on your forces. So we're going to use this process from Blodgett's where you figure out if you can evaluate as a thin weld. We'll find the total force, we'll calculate our properties of that weld cross-section, and then we're going to calculate our weld size required. We've got this example model here. If we take a look at our picture of this, it's a simple model of a stoplight structure. It's something you see every day but never really think about, at least in my case. And we represented this with a thick vertical tube constrained at the bottom and a thinner cantilevered beam with some mass elements offset here. We've got gravity load and some little wind loads along our beam. Right now it's all set up to run as a standard analysis, but when we're pulling our free body diagrams, we need to make sure we request the output for free body diagrams. So I'm going to expand master requests and conditions and go down to our output requests, and we'll edit those to request our equation force and force balance. We'll analyze real quickly. And let's activate our results set and go to our post-processing tab. We'll go to our free body section of the post-processing toolbox and then select add our free body. And this will be our weld free body diagram. And we'll select all the defaults for now, and I'll change them in the free body toolbox. So now we get these new options. This is a welded interface, so I'm going to select an interface load. For my free body elements, all I need to do is select one of the elements along that weld. So we'll just grab that little beam element there right next to the weld. Select OK. And then we'll choose our node at the weld. Okay. Auto-locate our total summation vector. Yes, we do want it right at that weld location, so we'll select yes. And now we've got some vectors. By default, it shows us our total force vector and our nodal vectors, so we're not quite done setting up our free body diagram just yet. The first thing we'll take a look at is our free body contributions. We want to make sure that we're not including contributions we don't want. So I'm just going to go in here and turn off everything except for my peripheral elements. I only want the force in that location from the elements next to that weld. We'll minimize that. And I will turn off my force vectors for the nodal force because we just want our total summation here. It's not going to change anything, but it is going to clean up our display. And then for our total summation vector, I'll expand that and turn on my moment vector display. We'll turn on our components of that moment. So once we're here, we've got our force in the X direction from that wind loading we applied. We've got our vertical shear force from the gravity load on this structure. And then we've also got some pretty significant moments from this thing trying to twist, from it pulling down, and from it having that wind load on this big cantilever arm. Now, from here, we'll take these forces and go crank out some hand calculations based on what Blodgett gives us. And I've got a little MathCAD document set up here. And for each weld, you're going to have different allowable stresses, different geometries. So I definitely recommend taking a look at Blodgett's. It'll be included in our references, and really read through the treating a weld as a line section, and you'll want to create these documents for your own welds. And what we do is we take our geometry of that weld, we'll input those values, and then down here, we'll grab our forces and moments from that free body diagram we've created. With those forces and moments from FEMAP, we combine that with our, well, before we go there, we'll get our weld group section properties. So this is our, based on the geometry of that weld, we've got the perimeter, our distance to the neutral axis, and the section modulus. The section modulus information you'll find in Blodgett's as well. And this changes per your geometry. And from there, we combine our forces and moments with our section modulus of that weld geometry and get our resultant force at that location. And based on that, we can calculate the minimum weld required to handle that force and moment combination. And in this case, we've got a weld leg required that's over 1/2 inch, and our thickness of our structure is 0.28 inches. So this shows that the specified weld size for this component is not big enough. So in this case, we need to go in there and add some reinforcements. Now this is important because if we were to just look at our stresses from this model and ignore our free body diagrams, let's turn off our free bodies, and we'll go in there and contour our, right now we've got beam max combined stress. Let me move this thing over here. You can see that the stress is 17 KSI. And over here in our MathCAD docs, we're calculating this with a maximum stress of 20 KSI. So even though our stress at that beam with that cross section is only 17 KSI, our weld stress calculations based on the force at that location show that our structure is not going to be strong enough with that weld. So that's important to keep in mind. You can't just look at your stresses and trust them. So that's our beam models. Let's take a look at our plate-to-plate model. And in this case, we've got these nodes merged along this location. And the setup is pretty similar. We'll make sure we've got the right output requests. And it looks like we've got equation force and force balance, so we can just analyze that. Now, this model, before we get into adding our free body diagram, once we've got our welded location there where we know we're going to be pulling weld forces, when we're treating our welds as a line, we're going to evaluate it in terms of force per inch. So it can be really useful to have a consistent weld sizing that's easy to translate into a nodes per inch value. So if we just measure the distance here, let's see, oops, it looks like I grabbed the same nodes. We'll measure there to there. You can see we've got a 1 inch distance. So we've got 1 inch node spacing. So when we're pulling forces on these nodes, we automatically have our force per inch. So with our results, we'll go in to add our free body, new free body diagram. And this time we'll take some shortcuts, weld free body diagram. And we know it's going to be an interface load, so we'll check that box. We know we want peripheral elements, so we'll turn off everything except for our peripheral elements. And this time, instead of grabbing our total force, we'll turn that off. We only want our nodal forces, so we'll leave that guy on there. Select OK, and done. Now, we have to be a little bit more careful with our selection on our elements and nodes in this case. So for my elements, I'm just going to grab, all you really need to grab is all of your elements along this weld, but I'm going to make this easier by selecting all of my elements on the surface, and we'll grab that, whoa, I got labels on accident, sorry about that. We'll grab all of the elements along this green surface there. And so that's going to include the elements alongside that weld. So select OK. And next we need our free body nodes. And this time we're going to grab all of the nodes that are welded here. and we'll select method on curve and grab all of those nodes, or all of those curves that are at that welded connection. Okay, and we'll just include our total summation vector even though we're not looking at it. And now we've got our vectors at each of the nodes showing our forces. Now it's kind of hard to tell what's going on here. I'm going to change our nodal vectors from components over to our resultant. And now you can see a little bit better about which direction these forces are going. And you could go in here and turn on your labels and do your same hand calculation for the welds at each node that we looked at for the beams. But there is an easier way, especially once you start getting hundreds or thousands of nodes that are welded. Once I've got this information here, there's a free body tool that says list force balance. I'll choose that, and this is going to copy all those forces at the nodes that I have in my free body over to either message window, data table, or the clipboard. And I want to grab all of my calculated nodal sums along that welded location, so we'll check that box. And data table isn't an option right now since I don't have my data table turned on. So I'm actually going to cancel out of this real quick and turn on my data table. So tools, data table, and we'll try that again. Here we go. We'll check our list calculated nodal sums, uncheck the contribution details, and we'll list this to our data table. Select OK, and yes to unlock. And now each of our nodes that's included in that free body diagram has the total sum of the forces included here. So we've got our X force, Y force, and Z force. We could save this as a CSV file and bring it into Excel. I'm going to shortcut that a little bit and just select all of them and copy. And then I've already got this Excel document made up where I can just paste it right in. Oops, it looks like I grabbed a little bit extra. So we'll just delete that extra information. And might as well just delete these rows. So the first thing I do is get the resultant force at each of those nodes, and then I calculate my weld size, and then you can do all of your nice tricks with your Excel programming where you get your max size, you can list your max weld magnitude, you can change your allowable of that weld, and quickly process all of these welds. So we're running pretty close to the end here, and we want to have time for some questions. So maybe I'll just show the last post-processing on this model, and we'll leave the last model in there as a little bonus for you guys. So when we look at this, I think the thickness of this is 1/2 inch, but let's say we want to highlight any weld that has maybe we know our max weld force for a given allowable is 250 pounds per inch here. And in that case, it can be tricky to go into our Excel document, look at our weld forces, and then grab the nodes. Like you could grab the element IDs or the node IDs and go back to your model, but that can be a little bit painful. We can quickly highlight the nodes that have forces greater than our allowable force by choosing our minimum vector magnitude to be shown. And right now it's set at 1, so it's showing all of these forces that have fairly high values. I can change that to, let's say, 250 pounds. And now that quickly got rid of all of the nodes that have really low nodal forces and isolates those nodes with higher forces that we might need to be concerned about. And maybe if it's 500 pounds, you can see only the ones that have issues are right at the edges of this I-beam. Another way to clarify your forces and really get more of a qualitative look at what's going on, if we turn off our values and expand our length option in the view properties window, we can scale by magnitude. And this is really nice because you've got your large forces around the edges here, you've got your smaller forces in the middle, and then once you've got this view, you can see maybe this region in the middle along the neutral axis of your beam isn't really an area to be concerned about, but these areas on the edges are a little bit worrying. And you can play with that in this last model that we were going to include in our workshop files. And one last thing to note on this model is the node spacing along these welds is 1/4 inch. So in this case, when you pull out your forces along those nodes, you just have to keep in mind that you've got 4 nodes per inch. So your nodal forces aren't directly your weld force per inch. Adrian, do we have any questions to address in these last 5 minutes? You're on mute, I think.
Well, this is George.
George, you're pretty quiet.
Yeah. Oh, there we go. That's a little better. I've been looking at the questions and trying to answer most of them. There's still a few hanging out there. And then we got the one, what is the recommended book for fatigue and static stresses? Weld fatigue and static stresses, Kyle, Adrian?
I've got one here. I guess it all kind of depends on the different codes, but you know, one of them is Parker's Mechanics of Fracture and Fatigue.
That's my favorite.
But yeah, I guess there's, whether you're using the British standard or the international,
right.
What is it, the international welding, they're going to have different specs, will have different
right.
SN curves, different weld categories.
Oh, and don't forget Julie Banifield's book.
Julie Banfield, okay.
Yeah, I think I got the name, or Bannatyne. It's there on my bookshelf.
Okay, so
Metal
yeah,
fatigue.
I think we got a kind of a variety of different, like, detailed questions, but what I want to do with the last little bit here is just key points. You know, you want to set up the model so you get the right load transfer and the right stiffness, because if your loads are off, well, everything downstream is going to be off. So that's kind of step one. Step two is realizing that you don't want to chase these singularity stresses at the weld toe. So if you are going to go the stress fatigue route, per the different methods from the different codes, you recover stress either at the weld toe or one thickness or away, or, you know, the different methods will have different recommendations. Then you're going to use those stresses based on the weld type or weld category and find the corresponding SN curve. The other option, weld sizing, more of kind of a design guide like Kyle covered. You're going to extract your forces, and then you're going to have these conservative hand calculations to give you weld sizing. If you skip this step and follow the stresses in your model, you could end up with something that is not conservative, like his little stoplight example there. So really, building the model, running the analysis, those are just kind of the first steps in a bigger process. What do you think, George? Is that kind of...
Yeah, that would do it.
Excellent. Well, like I said, we're going to have some more questions and answers and try to incorporate that into to our documentation here when we get that uploaded. But I appreciate all of the input and feedback from the attendees. This has been great, and yeah, I think it'll just instigate more and more conversation and kind of digging, which is a good thing, because it's a massive topic. All right. Well, on that note, thank you all for coming. Yeah. Kyle, George, thanks for your help, and
Welcome.
we'll get this up on the website probably early next week. All right. Thanks, everybody.